have been, we were talking about input validation attacks. So today we will move on to a different type of attack which involves file names. Okay? So so what are these file name attacks, right? So you have so there are a couple of examples, and both of them take advantage of the fact that there are directories that are writable or readable by multiple users, right? And then if you have a multi-user system, then it's possible that this fact that multiple users can simultaneously access the directory can be the basis of some vulnerabilities. Okay, so think of a typical case. So there's application A creates a file in the /tmp directory, and maybe it creates a temporary file, and it maybe the file is named right, something like some strange name, and so the writer of this application has assumed that because this is so strange, it's unlikely that anybody else will be using it, so they just, the application goes ahead and just opens this file. Okay? The problem is that, again, the thing that we always have to keep in mind is that when programmers write code, they often have this sort of, random fault model of the world, right? That is, errors are, not intentional, or erroneous inputs are somehow not intentionally created. This is sort of the default model that most of the programmers operate with, and so this is why a lot of vulnerabilities come about. Right? The vulnerabilities come about because the programmer thinks, hey, this kind of error is never going to happen. Who's going to provide this type of input? And of course, the attacker's goal is to essentially invalidate the assumptions that the programmer has made, because by invalidating those assumptions, the attacker will be able to make the program do something wrong. Okay, so this is an example. The programmer thinks, oh, who's going to come up with some strange name like this, and you can imagine that the name can get much more strange, can get much longer and whatnot, and then the programmer may think, who's going to create this? Except that if it's an attacker, then the attacker figures out exactly how this file is being created, so that they can fool this program. Right? So in particular, even though I said multi-user system, on any operating system there are at least there is the administrative or root user, and then the normal user. Right? There are at least two users, and so because the root user has higher privilege, they can do things that a normal user cannot do, and by abusing these types of file name creation type of bugs, the attacker, who may have access as a normal user, may be able to do something bad, right? So for instance, if there is a file that is only root writable, then what the attacker can do is the attacker can create a symbolic link. Okay, so for instance, this name could be a symbolic link that links to something like so in that case, what's going to happen is that the program, if the application A is running with root privilege, then it'll open this file, and when it does that, it'll basically end up overwriting that file. Okay? So you can imagine that corrupting etc password is not exactly a useful attack, I'm using the name just to show that any file, could be overwritten by using this type of attack. Yeah.
If you need to create a symbolic link of a root user on file, you would need execute permissions on that file as well. So how would you execute that?
Why would you need that? Because /tmp, see, you are creating a file in this directory, right? So in order to create a file in the directory, you need a write permission in /tmp, right? Every user has write permission in the /tmp directory, and once you have that, you can create a link to anything.
But when you would run ln, the file etc password,
Yeah.
if it doesn't have execute permission, ln will not be able to create a symbolic link.
Why?
Because it can, the permissions only be held by the root for that particular file, the root user.
Yeah, you can link to anything.
But that's only for soft links, right? Not the hard links.
That's symbolic link is a soft link,
Okay.
right? So hard links have, good question. So on Unix, there are two types of links, okay? And this is not necessarily specific to Unix. Every operating system has this kind of a distinction. A hard link has, certain restrictions, right? So, a hard link, I should say, can only target a plain file, right? And and it must be in the same file system. Okay, so a file system is a concept that so you're if you do a default install of some Linux distribution, typically all the files will be in a single file system. Okay, but it's customary that on server systems at least, you often create multiple file systems, which means that they are completely separate, right? So you have pre-assigned how much space each of them is going to have, and they are completely disconnected. They have no relationship to each other. And hard links cannot cross those file system boundaries. And this is, again, if you are working with Linux on your desktop or a VM, this restriction is something that you will probably not even notice. Okay, but this is a restriction that you're going to notice. So a hard link always has to be to a plain file. Okay, a symbolic link, on the other hand, right, is something that just contains at a next level. It is just a plain file that contains target file's name, right? But there is a special flag on it that the operating system knows that the content of this plain file should be interpreted as a symbolic link. So normally the operating system, when you try to access that file, it will notice that it is a symbolic link, go read the content of this file and interpret that as a new file name and just go and fetch that file. Okay, so that's how symbolic links work. And symbolic links, don't have the restrictions of right. As a result, generally hard links are not that often used because those restrictions make it quite difficult to use. Okay, you can't have links across directories because you can't be sure in advance that those directories won't be in different file systems. So this restriction makes them difficult to use, and this restriction, of course, also makes them difficult to use. Yeah.
For the first restriction of found, what other type of file that?
You can have a directory, right?
Oh,
Right. So symlinks can link to a directory, but these won't stop. Okay. So because of these restrictions, very often most links that are on the system are symbolic links. Okay. And and since symbolic link is simply a plain file, right? So to create a link, you generally need permission to create that plain file. Okay. And so the attacker, or let's say you are the attacker, right? And you want to get root access on the machine, right? And you can imagine that if it is a server system, well, you may have user access but not root access, but you want to get root access. Then you could use one of these symbolic link attacks to elevate your privilege, right? You can see that, well, obviously this is not going to give you directly your root privilege, but it may give you the ability to do something that you would otherwise not be able to do. Okay, so in this attack, all that happens is that this application A is going to write into this file, and if it's already linked, then any operation to write this is going to end up being a write operation on that. Okay, so the attacker is able to overwrite a file that requires root access. Okay, so the second example is a variant. So in the second example, the attacker doesn't create the symbolic link, right? So what the attacker does is the attacker waits for the file to be created, right? And then later on, the attacker goes and removes this file. Okay? And because /tmp is a shared directory, so the permission can be set so that anybody can read and anybody can write. Okay? And therefore, even though the file was created by root, it could be deleted by a normal user, and now the normal user could set up this link. Right? So what is the difference between the two attacks? So in the first case, you have an application which seems to have an obvious problem, right? Obvious error that it doesn't check whether this file is already present, right? And then it just goes blindly opens it. So example 2, application A has been improved, so it's not going to create this file, randomly, right? It's going to check if the file is there, and because it's not there, it goes ahead and creates it, right? But still, the attacker can come and delete this file, and then recreate it, and now the attack is again there all over. So what we will see in a few more examples is that every time we try to make our program more secure, we realize that it still has problems. Okay, so once you do this, right, then you get into this more general class of bugs called race conditions. Okay, or in the case of file names, time of check to time of use attacks. Okay, so again, what was happening was that the application, the root application checks whether the file is safe to write in some sense, and then there is a check that's happening, and then after the check, it accesses that file, right? So between the check and the access, there is a small window, right? And in that window, the attacker tries to get in and change the file, right? So when the application checks the file, it looks good. But by the time it goes ahead and accesses the file, the attacker has come in and changed it. So again, the same attack could be thought of that way. So okay. So application A right? So it may have this logic. It checks whether f is not present, and then it goes ahead and opens f for writing, which on most operating systems, if you try to open a file that doesn't exist already, and you're trying to write to it, then this operating system will create the file, right? So what the application A wants is, it wants to create the file provided f is not already present. Now, what the attacker does is, let's just say, instead of, let's just keep using, let's see, password as the target. So what the attacker does is, they race with the program and try to get in the time period between these two, between the check and the time the file is open. And at that point, so what happens is that even though the application is checking, by the time it writes, the attacker has taken over, right? And of course, you would say, how can the attacker possibly succeed? Because it's so difficult to get in, right? And that's why, you know, you have to always realize that attackers always figure out a way. Okay, so we'll see how that happens in a little while. Okay, but the point is that anytime an application tries to protect itself, the most obvious way to implement that protection, that way itself has a vulnerability, which is this time of check to time of use window, right? So therefore, a race condition may persist. Okay, and the race conditions, there are several forms. So I kind of wrote pseudocode here, but if you look at the actual code of some system application, you will see that this operation, okay, so let's say, so these race condition attacks are often targeting what are called setuid programs. So what are setuid programs? Anybody knows? You haven't heard this term? Okay, so setuid programs are those which a normal user can run, but when that application starts up, it will start up with the root permission. So for instance, if you want to change your password, right, you will run a program on Unix called password, right? So the password program obviously has to update, some files which are only root writable, okay? But obviously a normal user should be able to change their password. So how do you do this? You write an application that has a file permission called setuid permission, okay? And what happens in that case is that when the program starts, its user ID is changed to that of the owner of the file. So your password program, which will usually be this place, sbin password, right? So this program will have a setuid permission, which you will see if you do an ls minus l on it, you'll see RWS. So you'll have the letter S in the place of the execute permission. And what that means is that it's going to run with the permissions of the file owner. Okay? So these are the programs that are most susceptible to this kind of race condition attacks, because the attacker can start those programs. So they know when that program is going to start, when, and therefore if they want to do a race, then it's best if they know when the program is going to start, and therefore when it might get to this point, right? So the setuid programs are the ones that are typically targeted. And so these setuid programs, because they are running on behalf of a normal user, right, they need to make sure that they aren't doing things that the normal user is not supposed to do, right? So for instance, so the form of the check would be if current user can access F, then open F. Okay? So on Unix, this is checked using a system call called access. Okay? And this opening uses a system call called open. So this is so the particular example I gave you is a race condition involving access and open. Okay? So there are other types of race conditions. So for instance, there could be a backup and restore program, which restores, let's say, which can back up your program and restore your program, right? So in order to, so typically this program will be a setuid program, but maybe because it has to write into some file partition that normal users shouldn't have access to. So the way this program will work is that when it restores files, right? Because it's going to be running as root,